Welcome, and today we're going to be looking at C1, which is elements, compounds and mixtures. First we need to look at some definitions of what are these terms used to describe. So an atom is the smallest particle that can exist. An element cannot be broken down into anything simpler using chemical or physical means. It's essentially one type of atom. A compound contains two or more elements chemically bonded together, and that means it cannot be broken down using physical means like filtration or crystallization only. We can only separate that using chemical means. However, a mixture contains two or more elements or compounds physically mixed, and this can be broken down by physical means like filtration or crystallization. A compound usually has two individual parts, and they both would have capital letters like H2O. That's a compound. It contains more than one type of atom. We've got the hydrogen and the oxygen. So we've got two types of atom, two elements, which make a compound. And a molecule is just when we describe two or more atoms that are chemically bonded. So this could be an element. It could be H2, hydrogen. Or that word molecule could still be also used to describe a compound like H2O. Okay, so the next thing we're going to look at is what we call the history of the atom, which is essentially how the atomic model, the current one that we use today, came into form essentially. So the first thing that we need to remember is that John Dalton was working in the early 1800s, and he is the guy who discovered the atom itself. Okay, so John Dalton comes first, and sometimes they might ask you to put the people or their discoveries in order as to which came first or who discovered what. So John Dalton discovered the atom. So number 2 was J.J. Thomson, and he was working end of the 1800s. You don't really need to remember that, but that's just to give you some context. And he discovers electrons. Now he uses what we call this plum pudding model. So essentially the plums, the little dots in the what he called the pudding, represented electrons, and the dough was represented positive charge. So the plum pudding model, the dough was the positive charge, and the little dots, the little plums, were essentially the electrons. So J.J. Thomson discovers the electrons. Number 3, Ernest Rutherford. Now he worked in 1909, and he discovers the nucleus. He uses the alpha particle experiment, in which he directs high energy beams of alpha particles into gold foil, which was 1 atom thick. Now he makes 2 discoveries. Number 1, that the atom is mainly made up of empty space, and number 2, that that protons must be concentrated within the centre of the atom in what he called a nucleus. And sometimes they ask you, how can we trust Ernest Rutherford's conclusions? In other words, how do we know that his conclusions were accurate? Well, that's because he did over 100,000 measurements. Okay. Number 4 is essentially Niels Bohr. Niels Bohr, 1914. He discovered that these electrons were then held at fixed distances. So in what we call energy shells, and we're going to look at all these terms: protons, neutrons, nucleuses, electrons, shells. We're going to look at that just in a minute. So number 4 was Niels Bohr. And finally, number 5 was James Chadwick. In 1932, he proved the existence of the neutron. Okay. Okay, so essentially when we see an element, on the periodic table, we generally have 2 numbers. So we have 1 number at the top and 1 number at the bottom. Now the biggest number is what we call the mass number, and that's the sum, so the 2 added together, the protons and the neutrons. So it's the sum of the protons and the neutrons. So, for example, sodium has a mass number of 23, and that's because it's got 11 protons and and 12 neutrons. And then we've got our smaller number. This is generally at the bottom, and this is what we call the atomic number, okay? The atomic number is the number of protons, okay? Because that's how we identify different types of elements. They have different types of, different numbers, of protons. However, what we need to know is that the number of protons in an element is exactly the same as the number of electrons in that element. So when we talk about the atomic number corresponding to the number of protons in that element, we could equally say that it corresponds to the number of electrons, because elements have an overall neutral charge, okay? The protons and the electrons, the number of protons and the number of electrons are equal, so they essentially cancel out that charge. Okay, so then we can draw this in a little table here. We have 3 subatomic particles, and this is just the overall title or group corresponding to protons, electrons and neutrons. So we could write that as pen to remember. Essentially, a proton is just a little tiny thing that has a positive charge, okay? You don't really need to know what that is, but you just need to understand that a positive charge is opposite to a negative charge, and our neutron has no charge at all. It's neutral. So if we look at a proton has a positive charge, and you need to know that it has a mass of 1. So because it's got a positive charge, we could say that one proton has a charge of positive 1, plus 1. Then you need to know the location of this proton. Where is this proton situated within the atom? Well, that would be within the nucleus, okay? The protons are found in the nucleus. And these are just really important fundamental details that might pop up on 1-mark questions relatively near the start of a paper. And it's just really good that we can pick up as many marks as possible. So it's really important that you learn the details here. And the next thing that we look at is a neutron. So a neutron also has a mass of 1. They sometimes like to ask that one. But its charge, we've talked about a neutron being something neutral, okay? It doesn't have either a positive or negative charge. It's got no charge at all. It's neutral. So its charge is 0. And where's its location? Where is it located? The neutron is also located in the nucleus. Then we have an electron. The mass of an electron is actually 1/2000th, so it's essentially almost 0. So you just need to remember that it's almost 0, okay? Its charge, we've talked about electrons having negative charge, so the charge of 1 electron would be -1. Where is it located? Now, the electrons in an atom are located in the shells. So the proton and the neutron is located, or protons and neutrons are located in the nucleus. It's only the electrons which are located in the shells. Okay, then we're going to move on to a tiny subtopic here called electron arrangement. And this is essentially how we write how chemists write the amount of electrons that are in each shell of an atom. So what we need to know here is that the inner shell, the first shell, is always 2. Essentially, when we have an atom, its first shell can always hold a maximum of 2 shells. And then for GCSE combined science, we then need to know that the outer shells are always 8. Okay, it's a little more complicated than that, but for our GCSE, we just need to know that it's a maximum of 2 on the first shell, and then for every other shell, it's a maximum of 8 electrons in that shell. So an atom can hold in its first shell a maximum of 2 electrons, and in every other shell, 8 electrons. So an example of this would be a question that would ask you to write the electron arrangement of, for example, calcium, okay? So we find you're always going to be given a periodic table in your GCSE exam and your mocks, which looks exactly like this. Okay, so for calcium, we'd essentially look up calcium on the periodic table. We can see here it's in group 2, period 4, and we look at its atomic number. Now we can see that its atomic number is 20. And we've been asked to write the electron arrangement of calcium. Okay, so we know that its atomic number is 20, which means that its number of protons is 20. And we know that the number of protons within an element is the exact same as the number of electrons within an element. So the number of electrons within calcium will also be 20. So to write the electron arrangement, we know that the maximum number of electrons within the first shell is going to be 2. So we need to fill the shells up to 20 electrons. And now 20 is bigger than 2, so our first shell is going to be filled, so it's going to have 2 electrons. So we're going to write 2. You then write either a dot or a comma to indicate that you are going on to the next shell. So I like to use dots. We then have the next shell, so we know that every other shell can hold a maximum of 8 electrons. Now 2 add 8 equals 10, but we want 20 electrons, so 20 is still more than 10, so we need to fill that extra shell because we're trying to work our way up to 20. So we've got 2 so far, so we're now going to add a full outer shell. We're going to put 8 electrons in that shell, so we've got 2 dot, and we're now going to write 8. So we've got 10 electrons now, and we want to get to 20, so we're going to add another 8 because the maximum amount we can add in this next shell is going to be 8, okay? Every other shell holds a maximum of 8 electrons. So we write 8. Now we add these up again. 2 add 8 is 18. Okay, so we need 2 more to get to 20. We need to fill the shells with 2 more electrons to get to 20. But we've got our maximum in that third shell. So we're gonna need another shell. So we put another shell on. However, we need 2 more electrons to get to 20. So we're not going to be able to fill this shell. How do we get from 18 to 20? Well, that's 20 take 18, which equals 2. So we're going to put 2 electrons in the outer shell. So we're going to write 2.8.8.2. And that is how you write the electron arrangement of an element, essentially. Okay, now see if you can have a go at writing the electron arrangement for magnesium and argon. Make sure you use your periodic tables to help, and pause the video here until you want the answers. Okay, so magnesium, if we look on the periodic table, we can see that the bottom number, the smaller number, our atomic number is 12, which means the number of electrons is also going to be 12. So when we need to write out the electron arrangement for this, we're going to write 2, 8, and then 2, and this is because we need to get to 12. We know that in our first shell, the inner shell can hold a maximum of 2 electrons, so that's going to be filled. And every other shell can hold a maximum of 8 electrons, so 2 is still smaller than 12. We still need to work up to 12, so we're going to add 8 into that next shell, and that brings us to 10, but we want 12. So how do I get from 10 to 12? I add 2 more electrons. 12 take 10 equals 2. So on my last shell, electron shell, I'm going to have 2 electrons. Then for argon, we can see on the periodic table that argon's atomic number is 18, which means the number of electrons is also 18. Okay, so we need to fill up the shells until we can get to 18. So our first shell is going to be full, that inner shell, which can hold 2 electrons, so we're going to write 2. Our next electron shell is also going to be full. We're going to write 8 there, and that brings us to 10. We still need 8 more to get to argon's atomic number of 18. So because 18 take 10 is 8. So our next shell is actually also going to be full. It's going to hold 8 electrons. So the electron arrangement of argon is 288. Okay, then we just have a few little facts that we need to be aware of because they might need to be applied to certain questions. So the first thing we need to know really is that the number of electrons in the outer shell, so the outermost shell of an atom, so the number of electrons that fill that outer shell is going to be the same. It's going to be equal to the number of that group. So for example, chlorine's electron arrangement is 287, okay? Its outermost shell has 7 electrons in it. That therefore means that chlorine is in group 7, so it directly corresponds to it. Okay, for example, sodium. Sodium has 1 electron in its outer shell, which means it's in group 1. okay? Periods are slightly different. So our group numbers are the numbers that come across the periodic table. So the vertical columns. So here we can see on the exact periodic table that AQA provided us in our exam, these little numbers at the top, 1, 2, and then over here to 3, 4, 5, 6, 7, and 0, those are the group numbers. This is telling us that everything in that first column going down has one electron in its outer shell, because every element in this first column, which is labelled 1, is in group 1, okay? Periods are slightly different. Periods go across, okay? So these are essentially our rows. So our first row would be this row containing hydrogen and helium. Our second row with lithium, beryllium, boron, carbon, etc. Our third row, our third period, sodium, magnesium, aluminium, etc. Okay, those are our periods. And what our periods tell us is how many shells an atom has. So hydrogen is in period 1. It's the first row going across. That means it has one shell. Okay, so we can use these numbers given on our periodic table to tell us how many shells we're going to have and how many electrons are going to be in the outer shell of that atom. Sorry. Now, all members of any specific group have similar properties. Okay, so group 1, atoms or elements in group 1 all have one electron in their outer shell, and this makes them highly reactive. This is because that one electron in its outer shell really wants to be lost, okay, and that's to gain a full outer shell of 8 electrons. This is essentially because the outermost shell on that atom has one electron. Now, when that one electron is lost, that entire shell is lost, which means that you go back down to the next inner shell, which is still full, okay? So, for example, when sodium loses its first, it's one electron in its outer shell, it will go back down to the next shell, which still has 8 electrons in it. And that's why the group 1 atoms and elements, group 1 elements want to lose that electron so that they can gain a full outer shell, which makes them stable, okay? And this is why group 1 is highly reactive and reacts with group 7, because group 7, we have 7 electrons in our outer shell, and to fill those outer shell, we want to gain 8 electrons, so we can gain that one electron that is lost from group 1 to get a full outer shell that means that when the element from group 1 reacts with the element from group 7, the group 1 element becomes stable because it loses that entire shell when it loses that one electron. So it becomes stable, and our group 7 elements gain that one electron, meaning that they have one more electron in their outer shell. They have now 8 electrons in their outer shell, meaning that they are also stable. So those two groups tend to react together, and those two groups are highly reactive. And you need to understand that group 1 is what we call the alkali metals, is the most reactive group. It's highly, highly reactive. We then move on to ions and isotopes. So this is so we're going to first talk about ions. So if an atom gains 1 electron, for example, so that's going to be our group 7. Our group 7 has 7 electrons in its outer shell, so it's going to gain 1 electron generally from those group 1 elements to become a full outer shell, to have 8 electrons in that outer shell. So now what we've got is we have 1 more electron than our protons, because when we gain 1 electron, we haven't changed our number of protons. And this means that that element now has an overall negative charge because it's got 1 more electron than it has protons. And you would say then that this atom has become become a negative ion. So what is the difference between an ion and an atom? Well, an atom has an overall neutral charge. The positive and negative charges, the protons and the electrons, cancel each other out, whereas an ion is charged. An ion is a charged particle. It has charge. It's either got an overall positive charge or an overall negative charge. Okay, so now what we need to know is that if we gain that one electron, we've got a 1- ion, essentially. So if oxygen gained one electron, we'd write that as O-. We wouldn't bother writing the 1, we just write the minus, O-. However, if oxygen gains 2 electrons, it has 2 more electrons than it does protons, we write O2-. If it gains 3, O3-, etc., etc. And what we can learn here is a quick rule that all metals are going to form positive ions and all non-metals will form negative ions. So let's look at our metals then. If sodium loses its outer shell electron, okay, it's one outer shell electron, our number of electrons within that sodium atom has decreased, it's gone down. Whereas our proton number has stayed the same. The amount of protons in the sodium atom has stayed the same, which means that we have less electrons than we have protons. So we have more protons than we have electrons. So sodium forms a positive 1 charge. So we'd write that as Na+. That's because it's got one more proton than its electrons. And then we have isotopes. So what is an isotope? An isotope is just an atom of the same element which has a different number of neutrons. So for example, we have different types of hydrogen and they just have different numbers of neutrons. So remember that our neutrons are found in the nucleus with the protons, and it's the sum of the protons and the neutrons which make up the mass number, which is usually the biggest number. And on our periodic table, it's going to be the top number. Okay, so if we have different numbers of neutrons, that will affect our mass number. So it will affect the mass of each individual element on the periodic table. So isotopes have the same atomic number as the other isotopes in that element. So different forms of hydrogen essentially have the same amount of protons, okay? They don't have a different proton number, they don't have a different atomic number, and this is because it's the number of protons that make something an element. So isotopes all have the same number of protons and electrons, it's the number of neutrons that differ, okay? So for example, there are 2 isotopes of carbon, okay? Carbon-12 isotope has 6 protons and 6 neutrons. However, the carbon-13 isotope has 6 protons and 7 neutrons, so that carbon-13 isotope is heavier. So essentially, all these isotopes do is have mass. They are overall neutrally charged. Their protons and their electrons balance out, so they don't really do anything other than add mass to, or simply just have mass, okay? Some extra neutrons will make the nucleus unstable and radioactive. However, not all isotopes are radioactive. Isotopes will have a different density, different physical properties, but will have the same chemical properties as the other isotopes of that element. So what is the difference between physical properties and chemical properties? Well, physical properties are essentially properties that you can see. For example, the colour of something, its density, its boiling point. Chemical properties would include stuff like flammability or corrosion. We're then going to move on to a little subtopic called separating mixtures. Now, the first technique that we can use to separate a mixture, remember mixtures can only be broken down or separated using physical means, so all of these techniques coming up are all physical techniques essentially. So the first technique is filtration. Now, filtration can be used to separate substances that are insoluble within a particular solvent from those that are soluble in that solvent. So what do all these fancy words mean? Well, insoluble just means a substance that cannot dissolve, whereas soluble is a substance that can dissolve. A solvent is like your liquid that you mix it in. A solution is when you have the dissolved substance in that liquid, in that solvent. So that would form the solution. So our example for filtration is generally sand from salt solution. Okay, so sand is insoluble. The sand, when you mix it in water or salty water, doesn't dissolve. Okay, so sand is our insoluble component. The solvent is going to be our salt solution. Okay, and they might ask you to describe an experiment to filter these. It's probably more likely to be a 4 marker than a 6 marker on this one. But you always need to list your equipment here. And we'd be using a beaker or a conical flask, and that would be full of our solvent, which is going to be the salt solution. In this case, we then pop in a funnel, and whenever you mention a funnel in GCSE chemistry, always make sure that you've put filter paper in that as well. So filter paper and a funnel, okay? And you just pour the solution, which contains the sand and the salt solution, through the funnel and the filter paper. And because of our sand particles are too large to fit through that filter paper, they're insoluble, they will be caught by that filter paper and they will stay in that filter paper, whereas our salty solution, our salty water, will filter through that filter paper and through the funnel and down into the conical flask below. And this allows us to then collect that sand by drying the filter paper containing the sand on it in an oven. Make sure that you say that last step, dry the sand in an oven. And that allows us to collect sand from salt solution. Our next technique is crystallization. And this, for example, could be used to obtain a sample of pure salt, which we call sodium chloride, from salt solution. So the first thing that you'll be needing to do here is to separate the salt from that water. And the best way to do this is to place the salt solution in an evaporation dish, which we're going to situate on top of a water bath. And a water bath is just a beaker of water which is put on top of a Bunsen burner and tripod and gauze. Whenever you mention a Bunsen burner, it's really nice to just use tripod and gauze. Sometimes it crops up on the mark scheme for and describe an experiment question. So we have a water bath and an evaporation dish, and they might ask you this actually, why would we use a water bath? And you need to say that then, if they ask you that question, that it is a gentler way of heating. Okay, it's a gentler way of heating the evaporation dish rather than heating it directly from a Bunsen burner. Okay, so it's a gentler way of heating. That's the key word there. Now, heating should be stopped at the point of crystallization, and they will accept that on the mark scheme without you needing to explain that. Just at crystallization point, remove from heat, But essentially, to explain what that is simply when the first crystals start appearing on the edge of the dish. So crystals start to form at the corners of that evaporation dish, or when half the solution has evaporated off. And then the rest of the water would then be left to evaporate off at room temperature, and that would leave a good sample of sodium chloride crystals, salt crystals essentially. And really make sure that you then say dry the crystals with a paper towel. Okay. Our next technique is distillation, and there are two types of distillation. We have simple distillation, or we have fractional distillation. Simple distillation separates the soluble solid from a solvent, collecting the solvent, okay, unlike in crystallization. So essentially, we've got something that dissolves, a solid that dissolves in a liquid, but we're going to collect the liquid. And then we've got fractional distillation, and fractional distillation just separates two or more soluble solids from solvent. Okay. So for simple distillation, a solution is heated and it boils to evaporate the solution, okay? The vapour given off, so for example, if we heat water, we're going to give off water vapour. That vapour given off enters what we call a condenser. And this is simply an outer glass tube which has cold water flowing through it that acts as a cooling jacket around the inner glass tube. And when hot vapour passes through this little condenser, which has got cold water flowing through it, so itself is cold, it cools the hot vapour. So that hot vapour cools and condenses back into a liquid ready for collection in what we call the receiving vessel. Any dissolved solids will remain in the heated flask. And then for fractional distillation, so we're going to use the example of crude oil. This pops up again in C9, so we'll look at it in more detail then. So essentially what happens here is we are heating crude oil, which is essentially how we make fossil fuels that we put into our car engines. So we're going to be heating crude oil. So the crude oil is heated and evaporates, okay? Now bitumen, which is a component of crude oil, which we will look at again in C9, has a really high boiling point, and that means it does not evaporate when the crude oil mixture is heated and is therefore collected at the bottom of the fractionating column. Okay, the difference between simple distillation and fractional distillation is that because fractional distillation is separating more than one component, it has this fractionating column which has different points. Different vapours with different boiling points can condense and then sort of filter off through little tubes, and we can collect each individual component, okay? So as the gases move up the fractionating column, they cool down, okay? Each fraction condenses at a different temperature because it's got a different boiling point. And that means that because it condenses at a different temperature, each fraction is collected at a different point. In C9, we look at how each fraction contains hydrocarbons with a similar number of carbon atoms. And essentially, the further up the column, the cooler it becomes, okay? However, the refinery gases, these are just components that have really low boiling points. They do not condense at all, and they simply pass out the top of the fractionating column, okay? If you see the term miscible anywhere, that just means liquids that dissolve in each other. And then we've got one more separation technique, which is chromatography, paper chromatography, which we do look at that again later on in the course. Okay, but just a quick recap. Soluble is a substance that dissolves. Insoluble is a substance that doesn't dissolve. Filtration separates insoluble from soluble substances. And crystallization separates a soluble substance from a solution. An aqueous solution, if we see that term aqueous, that just means it dissolves in water. And we're now going to look at paper chromatography. So paper chromatography works because some compounds in a mixture will dissolve better than others, okay? And the relative solubility, so its ability to dissolve, of the parts in a mixture in the solvent will determine how far up the paper each part will travel. So essentially we have a pencil line, and it's really important that we draw that line in pencil. And this is because if it was drawn in ink, that ink would run with the dyes or run with the mixtures that we are essentially testing with paper chromatography. We need to ensure that our water or our solvent does not cover the pencil line, because if it did, the inks or the mixture would dissolve into that solvent, okay? And I guess the other thing that we need to be making sure is that we are using a solvent that the mixture does dissolve in. If it doesn't dissolve in water, we want to be using ethanol. Okay, but the key thing that we need to know for C1 in paper chromatography is that the further up the paper, the higher the solubility of that component. So the dots that are closest to the line are the least soluble, and the dots which are most soluble will move the furthest up the paper, so they are closest to the top. Okay, the inks essentially separate into the dots, and that's because of a key example of paper chromatography is when we put a spot of dye onto that pencil line to see what colours make up that dye. So each spot is each different colour in that paper chromatography experiment. Then there's just a few extra notes that I've just written down here for C1. So a bit of a recap with some extra notes here. So the only difference between isotopes is that one will weigh more than the other. They have the same chemical properties, which means they do the same when they are reacting. So the only difference between individual isotopes is that one will weigh more than the other. Neutrons do nothing apart from have mass, okay? They make an isotope heavier. What's the difference between ions and atoms? Ions have different numbers of electrons compared to protons. Atoms are neutral. They have the same number of electrons and protons. Another note here is that any atom will try to fill its last shell to become stable. That's a key concept, which is essentially, the aim of C1 really is simply to explain a few chemical concepts to you in our first chapter, and then that's developed and used later on in later chapters in the course. So C1 is essentially just laying out different concepts in terms of the actual exam or mock papers, full mock papers. C1 generally has little coverage because it would more likely to be focused on the 2 markers. That's not to say it could be focusing like a 6 marker, but that would be the describe experiment usually, and that could be filtration or usually, fractional distillation could definitely come up. Another note here is that noble gases don't react with anything, okay? These guys are on our periodic table, they are labelled group 0, okay? These are our noble gases, and they have 8 electrons in their outer shell, which means they have a full outer shell, which means that they are very, very stable, so are really, really unreactive, and we can use the word inert to describe that. Dioxide, when we call something dioxide, that just means an oxide that contains 2 atoms of oxygen, whereas an oxide is any compound with 1 or more oxygen atoms combined with another chemical element. A molecule is a group of atoms bonded together, and a molecule represents the smallest fundamental unit of a chemical compound that can take part in a chemical reaction. Hydrogen is the lightest element, okay? They sometimes ask that 1 markers, and compounds have a fixed composition. That means the ratio of elements present is always the same in any particular compound. Now, I'm going to pop this in here. This is an equation that you do need to learn for abundance. So if a question asks you to calculate the relative atomic mass, and we can write that using the symbol AR, we will look at this again in C4. We need to use the sum of isotope abundance times isotope mass divided by the sum of the abundance of all the isotopes. And you might be thinking, what's abundance? Well, abundance is simply how rare an isotope is. But don't worry, the question will always say, so it usually is a percentage. They might say, has an abundance of 30.8% of copper 65, which is an isotope of copper, okay? So that means that 30.8% of all copper is copper 65. So what we do to use this equation is we'd put in 30.8 times 65, and then the question might have told us that 69.2% of copper is copper 63, so we then put plus 69.2 times 63, and we're going to divide that one by 100 because it's a percentage, and that will get us our answer. The next thing I'm going to do is to show you how to balance equations. So my first equation that I've got here is Mg in brackets OH close brackets 2 plus HCl makes MgCl2 plus H2O. Now this equation is what we call unbalanced because one side has more more atoms of an element than the other side, so we need to balance that to make sure that they are the same. So the way I like to do this personally to ensure that we don't make mistakes is to draw out a table. So we've got magnesium, oxygen, hydrogen and chlorine. So we list out all the elements that are in this equation, and then we just essentially make up a tally chart. We identify how many atoms of each element I've got in my picture here. So how many magnesium do I have on the side before the arrow, so the reactants? Well, just 1. Okay, those brackets, that 2 only applies to the stuff within the brackets. So in terms of how many oxygen I have on our reactant side, I have 2 because of OH is in the brackets, which means that 2 corresponds to that number there. So we're going to have 2. Make sure we write this as a tally. How many hydrogen do I have? I've got 2. That 2 still corresponds to that H within the brackets, but I've also got an H here, so I've actually got 3. And in terms of how much chlorine I've just got 1 chlorine molecule here. Sometimes people like to write a 1 in front of their equations. So if I've got no number in front of, for example, this hydrochloric acid here, HCl, that means I've just got 1 of that. So I've got 1 hydrogen, 1 chlorine here. And then we look at our other side, our product side. How much magnesium do I have? I've just got 1. Okay, that chlorine, right, that little 2 there only corresponds to the element that is directly before it. So that chlorine there, because it's only when it's in the brackets that and a little number would correspond to a letter that's before it, essentially. A big letter, because that would indicate an element. If we have a big number, for example, if I had a 4 in front of this HCl, that 4 would correspond to the hydrogen and the chlorine. It's a little bit tricky, these concepts, but just practice. You don't actually have to learn these rules individually. Just by practicing loads and loads of balancing equations, you'll be able to do it easily in no time. Okay, so the chlorine, how much chlorine do I have on the product side? 2. How much hydrogen do I have? 2. And how much oxygen do I have? 1. Okay, so then we need to compare these two sides. I can see that initially I've got 2 more chlorine here, so I might put a 2 in front of this HCl, and then we need to adjust our tally ratios accordingly. So I've now got 2 chlorines on my reactant side. I've also got 2 hydrogens here. So I've got 2 hydrogens here and 2 hydrogens here, so that would make 4. And then we look at, okay, I've got 4 compared to 2 chlorines and 2 oxygens compared to 1 oxygen. So I'm going to put a 2 in front of these products here, which means that I would have 4 hydrogens and I'd have 2 oxygens. And now we compare our ratios and they are the same, and that equation is now balanced. Just a little note here is that sometimes they give you gaps in past questions where they don't necessarily need to be filled. So essentially, be confident your answer might be right. So don't worry if there is a little gap for a number or a coefficient and you haven't filled it. That's fine. I'll post a link in the description to this video for more practice on balancing equations that you can have a go at if you'd like. But that is the end of C1.